Hey guys, this is Mr. Yo, and today what we're going to talk about is Lewis structure and shapes slash polarity notes. Okay. Now, there are three different aspects or notes about this, so please make sure to know every single detail about this note before moving on to the next. So here we go. Here are the couple things that we're going to talk about today. One is about the basic information, which is something that you guys probably have heard from our previous lessons. Next, we're going to talk about Lewis dot structures, which basically means drawing out shapes. Following, we're going to talk about bond types, and then the Vesper shapes, polarity, and let you guys work on the homework assignments afterward. So always remember, if you guys need to pause the video before going on to the next part, feel free to do so. Okay, so here we go. Basic informations. There are a couple informations that you need to know before moving on to Lewis dot structures. Number one is the octet rule. If you guys don't remember what the octet rule is, it's having a maximum of 8 valence electron. And if you guys don't remember which one has the valence electrons, well, the first column has 1, 2, and everything goes chronological order, skipping the transition metal, 3, 4, 5, 6, 7, and 8. So make sure that you know where or what the valence electron for each elements are. Okay? Next is ionic compound. Ionic, which we talked about last time, is basically a metal plus a nonmetal. Okay, so what does that mean? It means there is a positive charge and a negative charge. So remember that if you have a positive, that means you're losing electron. If you have a negative, you will gain electron. So I'll mark this as a note so that you'd remember which symbols represents which words. Next is covalent compound. Now, covalent compound is something we learned in the previous lesson. It basically means when we have a nonmetal plus a nonmetal. Now, we talked about saying that covalent compounds or covalent bonds do not have ions. They don't have a plus or a minus charge, which means they're going to share electrons instead of gaining or losing the electrons. So make sure that you know the difference between covalent compounds and ionic compounds. Next, we have the lone pairs. Now, lone pairs is something we haven't actually gone through last time, but it basically means a pairs of valence electrons, okay, that do not create bonds. I'll show you more example about it as we go along on this lesson, so stay tuned. Now let's talk about Lewis dot structure. So in the Lewis dot structures, there are some steps that we need to follow. Number 1 says write the symbols. Number 2 says place the dots, which represents the valence electrons, top, right, bottom, left. Now the order doesn't matter, but I usually just remember as the compass so that you remember where to plug in the valence electrons. Now note that 2 is the maximum amount on each side. So make sure that you remember that as we go along with these examples. But before that, let's talk about the valence electrons. Now, how many valence electrons will first column have? Well, just by looking at the first number, we can see it's a 1, so the valence electron is 1. If we look at 2, valence electron is 2. Now, jumping to group 13, what I usually do is for these numbers, remove the 10th. Or remove the 10s, I would say. Okay, so instead of 13, this will become 3. Instead of 14, 4, 5, 6, 7, and 8. Okay, so that's another easier way to remember the valence electrons. Now, there are some exceptions that you must understand before we move on to some difficult questions, which are the exceptions. The exceptions are that hydrogens can have a maximum of 2 electrons around it, while beryllium has a maximum of 4 electrons, and boron has 6. So you'll get to understand how to do this stuff as we solve some example problems. So make sure that you have these exemptions written on a piece of paper or in your notebook, wherever you keep your notes. Okay, so let's move on to the next part. Now, let's talk about some examples. So if we look at nitrogen, going on to your periodic table, nitrogen actually has 5 valence electrons. I'm just going to say E minus for electrons. Since nitrogen has 5 valence electrons, what I'm going to do is I'm going to make sure that I have 1 dot on each side. So we talked about having it north, south, east, west for compass, okay? Or top, bottom, right, left, whatever you guys want. The order does not matter. But the most important thing is before you move on to the second dots or a pair, you must make sure that each side has a single dot. So since we're only missing one more, you can place it right here, or you can write it, I use a different color just to show you guys, right here, or right here, okay, or right here. So it all depends where you want to place the single dot, but just make sure that you don't draw this many right now, but exactly 5 dots in total. So I'm going to make sure I delete these dots. All right, so next we have oxygen. So what I would like you guys to do is try it out on your own. If you guys have any questions, just make sure to pause the video and work on or try out the problem, and I'll show you the answer right afterward. Okay, so oxygen. If you look at the periodic table, oxygen has a total valence electron of 6. Okay, so we know there are 6 valence electrons. So like what we just did, now I'm going to try out a different way, which is just going in a circular motion or clockwise, whatever you want to call it. Okay, so there's 4 dots. Next, we have 2 more to go because 6 minus 4 is 2. So 1 and 2. Okay, so always make sure that you have, well, number 1, make sure that you have 1 dot on each side first. Okay, that's the first step. Second step is to add the electrons or add the dots. Okay, now where would you put the dots? Now some of you guys might, if I didn't show you this example, some of you guys probably might have written it like this. Okay, which is possible. However, you must make sure that the dots are right next to each other towards the central atom or to the center. Okay, so add the dots right next to each other. Okay, not on top, not on bottom, but right next to each other. And that's your basic information about valence electron or Lewis dot structure. If you have any questions, feel free to rewind and check these activities or problems again. and then we will move on to the next part. Okay? So here is your answers. Now, sometimes we also need to make sure that if we talk about lone pairs, which in this case are these are called the lone pairs. We do actually have to make sure that there's also something called as unpaired electrons, which means electrons that doesn't have a pair. So what we're going to do is we're going to count out how many electrons that doesn't have a pair. So in this case, we have for nitrogen 1, 2, and 3. So there are 3 unpaired electrons. Then how about oxygen? Try it on your own. Okay. So oxygen has 1, 2, and that is all. 2 unpaired electrons. Okay. I hope this is pretty simple for you guys to understand. So just make sure to review these before moving on to the next part. So if I show you the answer, just like where the arrow is pointing, those are the unpaired electrons. Okay, so now let's go on to the most detailed part. There are 2 methods of drawing the Lewis dot structure. For my standard kids, I would make sure that you guys follow this one if this is more comfortable for you. For my honors kids, you guys have a special method that you guys need to do, but that does not prevent from standard chemistry students to use honors chemistry students. Same goes with honors to standards. So here we go. Number 1 is to connect the unpaired electrons together only. So before we do that step, we need to figure out how many valence electron does bromine have. So bromine has 7. So I'm going to say Br has 7 valence electrons. So we have 1, 2, 3, 4, 5, 6, and 7. There is a reason why I'm drawing it in this format, but if you want to try out the other way, that is fine too. This bromine has 1, 2, 3, 4, 5, 6, 7. So once you get a concept of having 1 dot on each side, you can start out drawing 2 dots on each side first, which is totally fine too. But just make sure that each side has at least 1 dot. Okay? Next we have connect the unpaired electrons. So we talked about the unpaired ones, and it says put them together only, not the paired ones, but the unpaired ones. So the first element is written within the compound is your central atom. We can talk more about this as we go along, but just to make sure that you know that you need to first draw the valence electrons and then connect the dots. Just like this. Okay? So if you connect the dots, you will end up getting this picture. Now, it is very important that you guys understand the diatomic molecule which was in your previous test. So make sure that you remember these molecules for this unit. So if you guys are ready, let's move on to the next part. So now for honors. For the honors, it's really not that hard. I'm saying it's not as difficult as you think. Number 1, what you're going to do is find a total valence electron. In this case, we have bromine, which is 7 valence electron, but there are 2 of those. So that is a total of 14 valence electron. Oops, I spelled that wrong. Okay. And then what I'm going to ask you to do is divide them by 2 to find a total number of pairs. So that's going to be 7. Okay? So let's see what we can do. First of all, we know these two elements are going to combine together. So that is one pair right there. One pair. And then we're going to have 1, 2, 3, 4, 5, 6, and 7. And the reason why I'm circling is because those represents the paired electrons or the lone pairs. Okay. So that gives you a total of 7 bonds, or I should say pairs instead of bonds, because some are bonds, some are pairs. Okay? So that's another way to draw a Lewis dot structure. Now, this is more of a, I would say, more accurate way of doing so. When I say accurate, I mean you won't make much mistakes if you use this method. So it would be nice if you guys can all use this method to draw the Lewis dot structure. But if you're still confused, feel free to use this method as well. Okay? So let's move on to the next part. So the next part, which is a typo, I should have redid this before. We're going to go over the type of bonds. Okay, that is the next part. Now, if we talk about types of bonds, there are a couple things that you need to know. There are single bonds, double bonds, triple bonds. Not too hard, but always remember that a bond represents 2 valence electrons, or 2 electrons, whatever you want to call it. So in this case, a single bond will have 2 valence electrons. Double bond will have 4. Triple bond has 6. Okay? So as you can see that there is a big difference between these bonds just by the number of valence electrons. But there's also one more thing. If you can look at the picture below, the bonds that I created for you guys, you can see that the lengths are different. So something that you can keep in mind is that the more bonds you have, okay, the shorter the length of the bond. So that is a good information that you can keep that in mind for the test or for anything in general. Okay, so as if you get more bonds, it gets more tighter between the elements, which means the length of the bond will get shorter. So keep that in mind when you are going over these notes. Okay. Let's move over to some example problems. So for oxygen, if we have oxygen, okay, oxygen is a diatomic molecule, so we're going to have 2 oxygen, okay, and we need to figure out the number of valence electron. Now, I'm going to show the accurate way of doing so, which is having 6 valence electrons, but there are 2 oxygen, so that's going to be 12 in total. And what I'm going to do is I'm going to make sure that I divide it by 2 to see that there's going to be 6 pairs. So let's see what we can do. We have, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. As you can see, we have 2 unpaired electrons, which means the magic happens like this. Okay, so there are 2 bonds that are made together. And if we count out the number of pairs, we have 1, 2, 3, 4, 5, and 6, which means this is an accurate picture. So, but some of you guys might think that, oh, Mr. Yo, isn't it basically when you have two oxygens, you have one bond, and the rest are lone pairs? Well, this is the part where I'm telling you guys that this is incorrect. Here's the reason why. If you count out the pairs, oops, if you count out the pairs, there are 1, 2, 3, 4, 5, 6, and 7. But we said that there are 6 pairs. Why is there 7? That is why we actually try and figure out the calculation first before going over the Lewis dot structure. So make sure that you know how to calculate in order to figure out the drawings. So overall, the picture should look like this. Okay? It's pretty simple if you get used to it, but we do need a lot of practice before the test, and the test will not come out. It's not going to be pretty soon. So just make sure to practice these example problems. So I'm going to give you guys time to work on this. So please make sure that you pause the video and we'll go over the answers together. Okay, so let's go over these problems. So first thing first, we have oxygen dichloride. So remember, oxygen would be just O. Dichloride. Di means 2, and chloride is Cl. So we have OCl2. So what I'm going to do is, there's something that you guys need to know, which it did mention on the past notes, saying that the first element shown in the naming is called the central atom. Okay? Basically what it means is that it's the kind of like the backbone of drawing the Lewis dot structure, or somewhere it's being connected to. But note except hydrogens. Okay? So let's see. So oxygen has 6 valence electrons. Chloride or chlorine have 7. 2, 3, 4, 5, 6, 7. So if we do the calculation just in case, oxygen has 6 valence electron. We have 2 times the number of valence electron for chlorine. So that is a total of, let's see, 2 times 7 is 14. That should give you 20 in total electrons. But that means we will have 10 pairs. So let's make sure that the unpaired electrons are connected and count out how many pairs we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there you go. So we have 10 pairs, perfect picture. Next, we have phosphorus trichloride. Phosphorus is P, tri means 3, so Cl3. Now, we have phosphorus, which has 5 valence electron, and 3 times 7. And that should give you 5 plus 21, which gives you 26 electrons, which also gives you 13 pairs. So if I were to draw this out, I'm just going to quickly do this because we already went over how to do it. So here we go. Okay. And that's the drawing for phosphorus trichloride. Okay, so if you guys have any questions, feel free to ask me during class or send me an email and I'll try to explain it to you guys as simple as possible. So if I look at the answer key, that's what it looks like. Okay, so now let's go over the new material, another new material called Vesper shape. It's a short for valence shell electron pair repulsion theory. I'm not going to ask you for the full name or abbreviation of this, full abbreviation, but just remember as Vesper shapes. Here are things that you need to know about Vesper shapes, though. There are 5 different types of shapes. One is called linear, and then we have bent, trigonal planar, trigonal pyramidal, and tetrahedral. I'm going to explain this to you as much as possible and as simple as possible for you guys. But something you guys need to know is if we're asked to draw a Vesper shape, make sure that you don't draw the lone pairs. So do not draw the lone pairs. Now let's go over the shapes. Now, if we look at linear shape, linear is basically a straight line. That's pretty simple, self-explanatory because you guys have taken geometry. Linear means straight. And as you can see, we have 2 atoms and we have 3 atoms. So in this case, if I ask you how many atoms are bonded, there are 2. Okay, 2 that are bonded. But do we have any lone pairs? As in, do we have any pairs that are floating around the element? Well, the answer is no. Okay, you'll understand once I give you guys an example problem. Now, if I'm asking you about lone pairs, this is focusing on the central atom. Okay, keep that in mind when you're doing this. Now, bent, on the other hand, has 2 atoms bonded. Okay, 2 atoms bonded. But also, we have 1 or 2 lone pairs. And when I say lone pairs, I'm talking about these right here. Okay. Trigonal planar, sometimes I call it a fidget spinner. Fidget. I don't know how to spell fidget, but let's just take it as that. Kind of looks like a fidget spinner. So it has 3 atoms being bonded and 0 lone pairs. Now, trigonal pyramidal looks kind of like a triangular-based pyramid. Okay, so just by looking at it, we know there are 3 things that are being combined to the central atom, but there's going to be a 1 lone pair. Okay, just like shown right here. And then tetrahedral, which tetra means 4. So you're going to have 4 atoms bonded, but there's going to be 0 lone pairs. So if you guys understand how to do this and understand this table, it should really help you guys out of figuring out what kind of shape the compound is going to be. So here's some example. Here's the answer for the chart. So feel free to pause the video before you move on, and we'll solve some example problems and show you how we determine that. So here's a drawing of NF3. What does that mean? Well, we have a nitrogen, which is our central atom in this case. Central atom. And it's being connected with fluorine. So if the question says, what's the number of atoms bonded based on the central atom? Well, we have 1, 2, and 3. So we have 3 atoms being bonded to the center. Now, how many lone pairs do we have here on the central atom? Well, we know the central atom is nitrogen, and the lone pair we have here is just 1. So if you guys remember from the chart that we talked about from the previous table or previous slide, it says that the one with 3 atoms and 1 lone pair is called trigonal or trigonal pyramidal. Okay? If you spelled this wrong on the test, I'm totally fine with it. Okay? I just need to understand that you understand what these shapes represent. Okay, so that's an example of how to figure out the shapes' names. You will be solving a lot of practice problems on the homework assignment that I provided for you on Schoology. So just make sure to just go over those things. Okay, and there you go. All right, so let's talk about polarity. So polarity is the last thing that I'm going to talk about. Now, you should take note on this because there are some informations you need to know, but it's kind of simple depending on how you take it in. Polarity. Polar, if you can think about a magnet. In the magnet, we have north and south, positive charge and negative charge. So if we look at here, it says two atoms with different electronegativity, or we call it as asymmetrical shape, which you probably heard from geometry. Now, if I give you two of these pictures, or before we move on to the pictures, the nonpolar are the ones that have similar electronegativity. Okay, let me use a different color. Similar and different. So if we look at the picture on the bottom, which one matches which? So if we look at H and H, is this a polar or a nonpolar? Well, the answer is going to be nonpolar. Why? Well, because it's symmetrical. If I draw a line in the middle, it's the same left and right. So that's why this is going to be nonpolar. Now, if it's polar, which in this case on the right side, if I draw a line in the middle, well, first of all, we don't even have to draw the line because we have two different elements shown on the left and the right side. So in this case, we can definitely figure out that this is polar. So just remember, polar means different atoms. Nonpolar means similar atoms. Okay? So now that we know the Lewis dot structure, the Vesper shape, and now polarity, what if we put them together? So if we look at here, it says any tetrahedral shape or trigonal planar molecules will be nonpolar if all surrounding atoms are the same. So as you can see, we have, well, hydrogen, 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 hydrogen. First thing first, these two shapes, they don't have lone pair. Okay? That's a key thing. They don't have a lone pair, then that means they're going to be nonpolar. But we also have to make sure that all shapes around the central atom has to be the same. In this case, we have hydrogen, hydrogen, but we also have chlorine and chlorine. So that's why this is polar for that shape. On the other one, we have hydrogen, hydrogen, and hydrogen, but for the polar one, we have hydrogen, hydrogen, and fluorine. So that's a big difference in this picture. So even though they don't have lone pair, please make sure if the elements or the surrounding atoms are the same. Now, what if it was a bent and trigonal pyramidal, the one that has a lone pair? Well, they will be called as polar. Now, if you have a lone pair, automatically it's going to be polar. Okay? So make sure that you remember all four of these sections. So, tetrahedral or trigonal planar can be nonpolar because they don't have lone pairs and the surrounding atoms are the same. Bent and trigonal pyramidal are polar because they have lone pairs. Doesn't matter if the atoms are the same. Okay, So last but not least, we have linear. Linear molecules have nonpolar if both sides of the molecule are the same atom. So if it's a diatomic molecule, it's a diatomic, which in this case is H2, it will always be nonpolar because there are two same elements combined together. Okay. Now, if we look at left and right, left side is nonpolar. Even though you see a lone pair, these are not the lone pairs for central atom. Our central atom is carbon. We don't see any lone pairs. So these are going to be, or it's going to be called as nonpolar. But if we have two different elements shown on the right side, it's going to be called as polar. Okay? So always make sure about these polarity before you move on to understanding or solving questions about polarity. Now, otherwise, any symmetric molecules will be nonpolar, and any asymmetric ones will be polar. Well, that's what I already mentioned in the previous slides. Okay, so now that we have that, let's try out an example. Is this shape a polar or nonpolar? Pause the video and try to answer this question. All right, the answer is polar. Why? Well, even though our elements or surrounding atoms are the same, we do have a lone pair. So if we have a lone pair, it's always polar. Okay? Now, lone pair on the central atom is the one that we're looking for. So if you guys have any questions, just give me a heads up, send me an email, ask me during class. And that's pretty much it for today's presentation. So good luck. Try to work on the assignments that I provided you guys on Schoology. If you cannot do it digitally or draw digitally, just write it on a piece of paper and show it to me during class. Or take a picture and post it on Schoology. So good luck, and I'll see you guys soon.